In this lesson, you can see it's titled Scale Factor, so you know that's going to come into play. And so remember the kinds of things that scale factor dealt with. It dealt with similar figures. It dealt with dilations, and dilations was a way of making something bigger or smaller while preserving angle measures. There is another kind of way of making things bigger or smaller, and we're going to take a look at those transformations here. So in this example, we have a parallelogram drawn for us. They've already found the original perimeter and area for it. And in part A, we're going to take the x-coordinates and multiply them by 3, and then find the new perimeter and area. So let's begin. A prime will be at -6, -1. B prime at still 0, 1. C prime will be at 9, 1. D prime at 3, -1. And so let's kind of sketch out what this parallelogram would look like now. This point would still be in the same place. A would be way out here. D prime would be down here. And C prime would be way over here. So let's find area first, because goodness knows that's easy. Area, remember, is base times height. And the base of this parallelogram, if you were to count the spaces from -6 to +3, it's 9 times, and the height of this parallelogram is 2. So this area is 18. That kind of makes sense. And then let's find its perimeter. Well, let's deal with the horizontal segments, because those are easy. Each of those horizontal segments would be 9 units long, so I'd have 18 plus. And then these diagonal segments, I could either use distance formula or use Pythagorean's theorem, since Pythagorean's theorem is what distance formula is based off of. Myself personally, in this diagram, think I want to use Pythagorean's theorem. So this is what I'm describing. A prime B prime squared would equal 2 squared plus 6 squared. So that would be the square root of 40, which would simplify to 2 radical 10. And so since there's 2 of those, I would add 4 radical 10 to the 18 that I already had. Okay, so the perimeter just got really weird. Okay, let's continue. In part B, we're applying a different transformation. We're multiplying y-coordinates by 3 this time. So let's erase and start over. This time, A prime would be at -2, -3. B prime would be at 0, 3. C prime would be at 3, 3. And D prime would be 1, -3. So again, sometimes it helps to sketch things out. 0, 3, 3, 3, -2, -3, and 1, -3. So this would be this parallelogram. So again, let's do area first, because that's easy. It's base times height. The base is 3, and the height is 6. So that's 18 again, which still makes sense. Now for the perimeter, again, easy part is the horizontal segments. Those are both 3, and since there's 2 of them, that means I've got a 6 plus. And I got lazy and didn't label these segments, or these points, sorry. So A prime, B prime squared, badly drawn triangle, but you get the idea, is going to be 2 squared plus 6 squared again. So I already know that's going to be 2, radical 10. And since there's 2 of them, I'm adding 4 radical 10. Okay, so that perimeter is also pretty weird. So now, last transformation, we're going to multiply both coordinates by 3. That gives me 0, 3, 9, 3, 3, negative 3, and negative 6, negative 3. Area, again, is easier. Let's sketch out what this would look like again. Negative 6, negative 3, 2, 3, negative 3, 9, 3, and 0, 3. Area, again, is the easier measurement to find. That's going to be 9 times 6, which is 54. And that feels kind of weird, and we'll talk about that later. The perimeter now, let's also find. Same reasoning. A prime B prime squared equals 6 squared plus 6 squared this time. So that's square root of 72, which is 6 radical 2. And there's 2 of them, so I've got, my horizontal segments I forgot to figure out. Those are 9 plus 9, so that's 18. Plus, let me go ahead and put it in. Plus 12 radical 2. And, look at that perimeter. That perimeter makes quite a bit of sense because 6 times 3 is 18, and 4 radical 2 times 3 is 12 radical 2. But that area, that's still kind of weird, but we'll talk about that. So the changes that occurred in steps A and B, did the perimeter or area change by a constant factor? Perimeter, no. Area, yes. Multiplied by 3. And the perimeter in part C was multiplied by 3. And then it says by a common factor, and the word factor implies multiplication. So what did the area get multiplied by? Got multiplied by 9. Okay, whatever that means. We'll talk about that. Area was multiplied by 9. So now we're taking it out of the coordinate plane and applying it to just shapes. So we realized before that the area of a figure, if it's vertically stretched or if it's horizontally stretched, the area just gets multiplied by that number. Okay, so in example A, they found an area of the original figure that you see there, and then they multiplied the length by 2 and found the new area, and they found that the area was changed by a factor of 2. So in the original figure, when I find the area of this trapezoid, it's going to be 1/2 times, let's do it off to the side, base 1 plus base 2 is 15, and the height is 8. And so that gives me 60. In the second transformed, oh, let me write this in here, 60. Now it says, let's multiply the height by 0.5. So now in my transformed figure, I'm just going to write a 4 here, because that's going to be my new height. So it'll be 1/2 times base 1 plus base 2 is still going to be 15, but now I'm going to be multiplying it by 4. So it should make sense that this area is going to be 30. So when the height of the trapezoid changed by a factor of 0.5, the area of the trapezoid changed by a factor of 0.5. In this your turn example, they're asking us to find the area of the triangle with those vertices and then apply the transformation to find the new area and describe any changes that took place. Okay, so I don't have a grid up here, but if I look at where they would generally fall, -5, -2, -5, 7, and 3, 1. This is basically what my triangle would look like. And if you look at it sideways, you would see that this would be a very convenient length to use as our base. So area of a triangle we know is 1/2 base times height. So the base of that triangle is 9. And the height of that triangle is 8. So the area of this triangle is 36. Then it's asking us to apply the transformation and determine the new area. Well, what we saw a few screens ago was that if I multiply just one coordinate by some factor, in this instance it would be 4, then the area got multiplied by that factor. So even without doing the calculation, the new area will equal 4 times the old area. So it's going to be 144. And these are square units. And that's it. Similarly, in this diagram, the area of a rhombus is found by doing 1/2 diagonal 1 times diagonal 2. The diagonals are 8 and 20. So that's 80 square centimeters. And then it says, what if I multiply the width by 5? What will the new area be? The new area will be 5 times the old. So it'll be 400 square centimeters. Now we're looking at proportional dimension change. And so when we make a proportional dimension change, that means we're using the same factor to change all of the dimensions of a figure, which means what we're doing is creating a dilation of the figure. And remember that in a dilation, the figures are similar, right? So in part A, they found a circumference, and then they enlarged the radius, and notice that the area changed by a factor of 9, which is 3 squared. So the scale factor is 3, and 3 squared is how much bigger the area was. So let's use that thinking in part B. The perimeter of this figure, if we're using that it's a square, then these are 45, 45, 90 triangles, and that means this is 6 radical 2. Or I could use Pythagorean's theorem to find it. Either way, the perimeter is 4 times 6 radical 2, so that'll be 24 radical 2. The area, I can use area equals base times height. Since I already know that the lengths of all of the sides are 6 radical 2, I can take 6 radical 2 times 6 radical 2. Well, 6 times 6 is 36. Radical 2 times radical 2 is 2. And so the original area is 72. And then the transformed figure, if I multiply the height and length by 1/3, what will be the new perimeter and what will be the new area? All right, so remember from the first screen that when we changed all of the dimensions of a figure, the perimeter was just the original perimeter times that scale factor. So my perimeter is going to be 1/3 of 24 radical 2, which is 8 radical 2. So I mentioned in the circle problem in part A here that the area changes by a factor of the scale factor squared. Well, my scale factor is 1/3. 1/3 squared is 1/9, and 1/9 of 72 is 8. So the perimeter changed by a factor of 1/3, and the area changed by a factor of 1/9. So this table is kind of summarizing what we used in the last screen. If all of the dimensions are multiplied by A, then the perimeter will be P times A, or if it's circumference, it would be C times A. If all of the dimensions are multiplied by A, then the area is going to get multiplied by lowercase a squared. I know that looks kind of weird, but make sure that you're realizing that what happens is that the area gets multiplied by the scale factor squared. So what happens when we're looking at three-dimensional shapes? So in this diagram, you can see that they found the volume and surface area of this figure, this kind of pill-shaped looking thing, and then they transformed it by multiplying all of the dimensions by 2, so the scale factor is 2, and so notice what happened. The surface area changed by a factor of 4, which happens to be 2 squared, and the volume changed by a factor of 8, which happens to be 2 cubed. So that should kind of make sense based on what we saw in the previous screen. That area got multiplied by the scale factor squared. And since volume is a cubic unit measurement, taking the original volume and multiplying it by the scale factor cubed should just make sense. So, again, in this chart, they're kind of summarizing what I just said on the previous screen. That if I multiply all of the dimensions of a solid by A, then the surface area would get multiplied by A squared. And the volume would get multiplied by A cubed. So two square pyramids are similar, and if the ratio of a pair of corresponding edges is A to B, what is the ratio of their volumes? What is the ratio of their surface areas? Similar idea. If the ratio is A to B, ratio of their volumes, well, that's a cubic unit measurement, ratio of volume would be A cubed to B cubed. And the ratio of their surface areas would be A squared to B squared.